Hello, it's Scott Manley here with possibly the final part of my tutorial series for Kerbal Space Program. I purposely waited until the latest asteroid redirect mission release appeared before I did this one, because this is all about transferring spacecraft to other planets. We're talking about interplanetary travel here, and the developers made a number of improvements to this, which I hope will actually make the thing a little easier. Now, this is a relatively easy spacecraft to build. You've got to get it into orbit first, obviously. I'm going to leave that as an exercise to the reader. But it's, has an engine here, a little space probe on the front with some science experiments and a big parachute. But most interestingly, it has this LV-N atomic rocket motor. Now, this is a thing of mixed blessings, let's say. As an engine, it's actually kind of hard to build into your designs because it's so long that none of the landing legs will reach past it, so you can't really land on it. It is relatively low thrust, but the reason why it's interesting is it has a specific impulse of 800 seconds. Now, the best other engine in the game has only about 390. This is a measure of your efficiency, so this will get twice as much thrust, and actually over time it will get much better in terms of the amount of delta V you get. This whole thing here has something about 5 kilometers per second of delta V, and using nuclear rockets are a good idea for interplanetary spacecraft. Another interesting idea for interplanetary spacecraft is, of course, the ion engine, which recently got buffed in Kerbal Space Program 0.235. It has higher thrust now, but it's still only for small spacecraft. Now, I'm only sending an unmanned spacecraft because, of course, we are still learning this, and you really don't want to subject your poor Kerbals to getting lost in space. So let's come out to map mode, and we'll see what we're talking about here. So there is me orbiting Kerbin at about 100 kilometers. As I zoom out, we see the moon, we see Minmus, and we start to see this blue line, which is the orbit of Kerbin around the sun. So from here, we can see that Kerbin orbits the sun, and then next to it is Eve and Duna. These are the two nearest planets, and these are two really good destinations for the first-time interplanetary missions. The reason is they are close, therefore they do not need very much delta V. They both have atmospheres, therefore you can use parachutes for landing. However, to be aware of this, that Eve has much higher surface gravity and a very thick atmosphere. If you have parachutes, it is very easy to land on it. However, it is very hard to lift off and return into space from it. It is a major challenge. Duna, on the other hand, has a very thin atmosphere, which means you'll probably have to use parachutes combined with engines to land safely. However, getting back into space is a whole lot easier. Both of these also have moons that are worth exploring. Now, these are two good places for first-time flyers. I would not recommend Moho because it actually needs a lot of fuel to get there, and it's on a small eccentric orbit. Similarly, Dres, it's not that interesting and it's a long way away. But Jool, although it's one of the furthest and most distant planets, it is a good target for the first-time flyer because it has such mass. Its sphere of influence is very large, therefore it's a lot easier to get close to Jool and get an encounter than it is to get an encounter, say, with Duna. Elu as well, don't even bother going, it's too far away. So, let's take a look at this system. What we want to do is go from Kerbin's orbit to Eve's orbit, for example. What we're going to have to do is we're essentially orbiting Kerbin at 100 kilometers. And so if we fly out with zero velocity, if we just escape, we will be on the same orbit as Kerbin. We want to go with enough velocity that it slows our orbit down and eventually crosses Eve's orbit, and hopefully crosses at a place where Eve just happens to be. And that is a lot of that is just to do with timing. So I've put this in a pretty good position. For Eve, you want to have roughly an equilateral triangle. So what you want to do is you want to draw a line from Kerbin to the sun, and then when you draw the line through Eve to this point on Kerbin's orbit, this should make something that looks close to an equilateral triangle. That is a rough approximation. There are many better tools to help you out with this, but that's what you want. And moreover, of course, you want Eve to be behind you and catching up. And the reason is, as you travel down on this orbit and arrive at Eve's orbit, that orbit is going to is going to start at Kerbin and is going to end at Eve. Therefore, the average height of that orbit is going to be higher than Eve. And because the average height is higher, that means it's actually slower. So by making it start behind you, it gives Eve a chance to catch up and hopefully meet you on the other side. The most efficient way to get from one planet to another is to have an orbit that just touches at the other side exactly when the other planet is passing. If you cross here and the Eve just happens to be there, that's great. That'll work for you as well, but it might take a little more fuel. Anyway, let's zoom back in and imagine how we're going to do this. So we have to slow down our orbit. We are orbiting around like this, which means we need to go off to the right. So I'm going to put a maneuver node here, roughly about 45 degrees compared to the day-night side. And I'm just going to drag this out, and we're going to see what happens. Watch this. Drag it, and I should probably bring up my map here. And you see it's already got some velocity on it. Now, I should start zoomed in. Yeah, as we zoom in and watch this, you see our orbit gets more and more eccentric. That would be as if we were going to the moon. Going a little further out, that would be as if we were going to Minmus, but we keep going, and now we are in interplanetary space. And because we're going backwards, you see that our orbit drops down a little towards Eve. Well, let's keep this going and go all the way down until we get pretty close to Eve's orbit. Well, that's pretty close. You know what? We want to know how close we're getting. Do you know how we do that? We select Eve and we say set as target. Well, now it'll show you this target or this predicted orbit relative to Eve. So the first thing to see is, although we were kind of lined up from some angles, we weren't lined up from other angles. So what I'm going to do is come in from this side, right? Because you're dealing with various levels of scale, you'll find that the maneuver node can be kind of hard to manipulate at times. So let's try grabbing this again and pulling our orbit in and seeing if we get a close approach. No, we're not getting that. And this thing wants to go. This is going to be a slow and tedious process in many ways. I'm going to zoom back out again. We're trying to get an indication of a close encounter just by dragging this thing in. See that? We're going to cross... Oh, there, you see? So this is the descending node. This is, of course, where the two orbits cross. And what we see here is closest approach is when we're here, but Eve is going to be behind us, which means that we need to adjust our orbit so that we arrive at this node later. How do we make ourselves arrive later? Well, we are starting here and we're kind of falling downwards. So if we actually start going upwards a little and then fall down, then that should delay our arrival, which means Eve will get there sooner. So because we're slightly ahead, this is what we'll do. We'll take our orbit and we'll adjust our exit here. We start here and we go out like that. We're going to make it go over this way a little. And that way it'll actually kick our orbit up and then delay our arrival. This is kind of complicated, but you'll learn it. And so you can grab the maneuver node and move it like this. You see that? So I've moved it a little, but I've lost the encounter. So I need to grab this again, correct it. And how close are we? 1 million kilometers. Can we get a little closer? Drag it. And then accelerate. Now we're down to 682,000 kilometers. That's pretty good. Let's do this again. Ooh, 151,000. And just bring this back. Oh, 200,000. You know, if I do that, what'll happen is if the positions are not close enough, then you will not get a predicted encounter and you'll have to go and adjust things again. Oh, so now we're actually coming past it. So that should be good. If we accelerate... Okay, so that's 108,000 kilometers. But the reason we're missing this is because we're going to actually pass over the top there. You see that? Oh, actually... Yeah, so we're passing slightly in the wrong plane here. But that's okay. What we can do is make a correction when we're further out here. We can add further corrections. And forgive the cat in the background. He is just being annoying because he wants food or something. So you're going to grab these, and one thing you can do is lift this up. See that? And that moves the descending node out that way. So we're adding a little more, a second maneuver there, and that's us. We would have a hypothetical encounter with Eve. So you would make the one burn to escape, the second burn here to correct your final approach, and then when you got there, you would make a braking burn to put you into orbit. That's great. So there's the principle. You're going to put things in roughly the right place, and then you're going to make these burns. Now, let's actually talk about how we would get to Duna, right? I'm going to kill these maneuver nodes, both of these, right? Because Duna is here. And, well, if we try to get to Duna, we're going to have to go the opposite direction, aren't we? Right? We're going to have to accelerate our orbit. And we're going to come out here. We're going to have to accelerate our orbit up and arrive out here. But... here's the thing, Duna is behind us, and it is actually moving more slowly than us, and because our orbit will be smaller, it will actually take, by the time we get there, it will maybe have got to there. But let's just take a look and see how this happens. So we would start, say, here, add a maneuver, accelerate out, and there we go. How far? Oh, look, we've already crossed its orbit, and we are in the middle of nowhere. I will maybe target Duna so we can see where our orbits end up. There we go, look. So it's predicting a close approach there, and the target would be way around there. So what we need to really do is adjust our time, right? We want to wait until Duna is in the right position. Now, what is the right position? The right position will be roughly 45 degrees. So Kerbin, the Sun, and Duna should be about 45 degrees. And this comes from a bunch of tools. There's one which is a website. It's called ksp.olex.biz, and that's a nice little web tool that figures these angles out. So we're in low orbit. We can time accelerate, but look, it says that we can only time accelerate at 50 times normal speed, so this is not the best way to go. Let's go to the Space Center and employ one of the nice new features which was added in the most recent version. In the Space Center we have time acceleration, so we can go to the tracking station. And we can start time accelerating. Off we go here. So we're probably going to need about 100,000 times time acceleration, and I would suggest that you rotate. So we're going faster than Duna, right? Duna is rotating, we're rotating. So we want to actually wait until we're roughly 45 degrees behind Duna, and the reason is, of course, we are moving faster. This is going to take a long time. Now, another thing that was changed in the most recent release is that by default, Kerbin days are used. If you notice the days that are being counted off, you're not getting double-digit days. That is because a single day, a single rotation on Kerbin is 6 hours rather than 24 hours. There are 4 Kerbin days in a single Earth day. Okay, we're now about 90 degrees behind Duna, therefore we are catching up. We still want to get a little closer. It doesn't have to be totally exact, right? Basically, if you get it perfectly exact, then in theory you can get a perfect transfer using the least amount of fuel. But in reality, you have quite a bit of leeway, and you're going to be using quite a bit of leeway. Ideally, you want to encounter the planet on the opposite side of its orbit, but that may not be possible because of inclination changes. Okay, I think that is close enough for us. I'm saying that's close enough to 45 degrees. So let's go to Interplanetary Probe and plan a mission to Duna. And once again, we return to our space probe, which has been orbiting Kerbin now for 2 years and 94 Kerbin days, waiting for the correct departure window for Duna. Now, One thing I should have mentioned previously, incidentally, is that assuming you're orbiting in the same direction as the planet rotates, if you want to go to an inner planet such as Eve or Eve or Moho, you want to make your escape burn on the daytime side. If you want to go outwards, you have to make your escape burn on the nighttime side. So if you're going towards Duna or Jewel, it pretty much has to be roughly around here. Now I'm just going to plonk that in there and drag it out until we get an escape vector. There we go. So that's showing some maneuver heading out into deep space, and it's actually getting pretty close to Duna's orbit already. So let's bring that out there. Now, to of course get the close approaches added, we're going to set that as a target. Note that the ascending node and descending node are about as far away as possible, which is never a good thing. You want your ascending node and descending node to be in the right place, but there's only so much you can do. Okay, let's try dragging out this. Oh, there we go. We get a little encounter. Now, what I want to do is try to minimize this, and I can drag the orbit back and forth here. And that's, yeah, if I'm moving it in this direction, that's working pretty well in terms of minimizing it. The only thing is, by dragging it forwards, I'm taking a little more fuel each time. Okay, so let's do that. So, how are we doing? 158. And what I'm doing here, incidentally, in case you're wondering, is I'm bringing this periapse in, which means it's actually moving faster around the orbit for part of it. And by doing that, I'm actually bringing the approach time forward, which means we're going to be there when Duna is there. Now, of course, you might have to move it in the opposite direction. It really is going to be a case of experimenting. You will get a good idea, generally, of what way you need to move things once you've been using it for a while. And you can see that it's not taking a huge amount of fuel or a huge amount of extra delta V here, but it is making the orbit less and less perfect. 609,000. Look at this. We're really... How close are we? 461,000 here. This is the closest we get. 224,000. And we're somewhere in the sun here. Look, we can eclipse the sun there. 260. And the game is getting a little confused. 159,000. 175. Oh, let's bring it around just a little more. 110,000. 109. I think that's about as close as we're going to get on this departure. See, the problem I've pointed out is that our the ascending and descending nodes are in the wrong place. Okay, so I'm going to do this maneuver, and it's going to take a little bit of time. One thing to be aware of is that if you're using the nuclear engine, they're pretty low thrust. So you probably need to burn a little ahead of time. So I'm just going to fire the engine for a minute. It says this burn is going to take about 2 minutes. Therefore, I am going to wait until I'm about 1 minute and 30 seconds ahead of time. So I'm looking at T-2. Let that get down to T-130. Okay, fire up the engine, and that's pretty good actually. So I'm going to run it slightly lower thrust until we get closer to until we get closer to splitting this, right? So I'm hoping that my estimated burn will match up a little better. Okay, that's us. Let's continue. So we're just going to fire out on this trajectory. This trajectory, however, that you have predicted is not going to be exactly what you end up with, right? The maneuver nodes are based on the assumption that you burn all your acceleration in one single moment. Because we're not able to do that, you're going to have to make course corrections later on to account for this. So anyway, this isn't such a bad encounter. And then what we'll do probably is around the descending node, we'll make a correction to the plane, and then we'll make a final correction to make sure we encounter. But I'm just going to make sure this actually happens. And we can time accelerate, of course, holding Alt and time accelerate. Once we get closer to the actual moment, we'll stop the time acceleration because you want to get this as accurately as possible. Messing this up will only increase the amount of fuel you need to burn later to correct for the arrival time. So here we go, 20 seconds. Oh, there, and we've escaped. And I'm going to slow down my time acceleration. Chase this blue dot. And then as we get closer, it says, oh, stop. There we go. How close are we? We're still about 200k. So I'm going to just try and get this 1 less meter per second, which is pretty easy with a low thrust engine. Okay, that's us. Let's kill this maneuver node. And so it actually says that we're going to escape and we're going to encounter this. So let's actually head out. Let's actually create a maneuver node here after we've escaped the system. We're going to escape the system first. That's what I'm going to do. So it's a good idea to disappear into deep space and then figure out your course corrections. And the reason is that every time you cross the sphere of influence, there is a conversion factor that goes into things, which can mess up your math a little bit. So once you get into deep space, things become more stable. And we're going to cross into deep space. Now, there we go. You see how the nav ball flipped? That was because we switched from being around... the nav ball switched from being referenced relative to Kerbin to a reference relative to the sun. So I'm going to click on this descending node. It says DN, descending node. And the first thing I'm going to correct is the inclination. I'm just going to drag this up, and you see how that flipped around? Well, I'm going to try and put that node close to the target orbit. See, it says not a number. NAN is about as good as we're going to get. Now, we are still not arriving at exactly the right time. So you see that we're kind of interior to it, so we should probably increase our speed a little. And you're just going to watch these numbers. And what does it say? 219. 219 is better. 198 is better. And we've lost our encounter for some reason. The game is not sure. It's only showing me sometimes. Come on. Well, 53,000 kilometers. And there, look, we get the magic encounter. So that's adding a maneuver right there. It's going to be 100 meters per second. And that will ensure that we actually arrive at our target. So point along this and skip forward 100 days. And of course that happens relatively quickly. Okay, we're almost there. 5, 3, 2, 1. And you know what? We're pretty close here. It's not a huge... When you're in deep space and you've got 100 days between burns, if you get it within an hour, that's pretty good. So I'm just going to make this burn now. It says it's about 100 meters per second, but accuracy is actually pretty important here in terms of the amount of burn you do. You don't want to mess it up, not like a Mars orbiter, the Mars orbiter that messed things up. There we go. How do we get it? Oh, look! So we're going to arrive at Duna. And of course, once we're there, we're going to perform a braking orbit. Let's do that, just so you understand that we want to follow this through. And once we get close to Duna, we want to make a burn to stop ourselves and let ourselves get captured. You can also use aero braking. You can use a gravity-assisted capture if you really know what you're doing. But simplest is simply firing your engine to slow yourself down and get captured. So here we go. We're going to fly past. You see this is the transition. It's 3 days away. 3, 2 days, 1 day. And of course these are Kerbin days. 2 hours. And you want to... Well, let's just do that. So there we go. Best place to get captured is of course at Periaps. So we're just going to do that. Just travel to the Periaps location. Look at the nav ball. And stop time acceleration. Turn the spacecraft around and fire our engines retrograde until we have captured ourselves into orbit. We're traveling about 1 kilometer per second relative to Duna, and we are actually pretty high altitude, so we'll probably have to burn off most of this velocity. We'll probably have to burn off about 1 kilometer per second to get captured. But after that, we can then try, landing the spacecraft in the various locations or whatever. But that really is up to you. I'm not going to show you how to build landers for these planets. That is half the fun. I was really just trying to cover the navigation and what is needed to really navigate things correctly. And there we go. That's a successful capture into Do Not Orbit. I'm Scott Manley. Fly safe.